According to good. And the little camera, is it going to, yeah, it's going to focus. Okay. So lots of stuff to get through today, because today we start NP completeness, which is sort of the good stuff. I mean, the rest of the course is also good, but this is the really good stuff. So this is sort of the, I would say the two best parts of this course, and therefore of your undergraduate education in computer science, are Cook's theorem and the halting problem. The halting problem, if you haven't seen it already, which you should have according to the ACM curriculum, but if you haven't, we're going to see it at the end of the course, along with diagonalizations and fun stuff like that. Okay, so Cook's theorem, which is also the P versus NP problem. So that happens today. Cook's theorem says, and we're going to cover the proof of this in the next class. But for you to understand what Cook's theorem, and this is the same Cook as in Tomb Cook. Remember, he did his PhD thesis on complexity of multiplication, and then he went on and did in the early 70s this paper about NP, P versus NP. He's a professor now emeritus, I think, at the University of Toronto. He was my logic professor when I was in grad school. Okay, so he says, so SAT is NP complete. So that's the short version, but you don't know what NP complete means yet. So this is great. After these classes, we're not going to have to talk about boom problems and clink problems anymore. So this is recording. I'm just going to make sure this. We're actually going to be able to use nice technical terms that people outside this course would recognize. So what does this mean? It means, well, okay. NP complete means SAT is in NP and complete for NP. But you still don't know what NP is. So this means given a Boolean formula, and a truth assignment, we can check if the truth assignment makes the formula true, we can check in polynomial time. It's clearer if I write the in poly time here. Makes the truth assignment true. So that means it's in NP. So if somebody gives us a solution to this, SAT is the language of Boolean of satisfiable Boolean formulas. Okay. So if somebody gives us a Boolean formula, which you know as like P and Q or R and not S or Q, all and S, something like that. Okay, so I don't know if this is satisfiable or not. But if somebody gives us a formula like this, which you should have seen this kind of thing before, and gives us a truth assignment, we can check if the truth assignment makes the formula true in polynomial time. So if somebody gives us a formula and says, this formula is satisfiable, here is a satisfying truth assignment, we can check if it really is a satisfying truth assignment in polynomial time. So that means it's in NP. NP is the class of problems for which we can check a solution in polynomial time on a standard computer. So shouldn't have drawn this here. So this part is SAT is in NP. NP is the class of, formally it's the class of decision problems. Oh, I forgot to start the timer. Oh, I have to pause, reset. We're gonna have to make this 20 minutes. Okay. Class of decision problems for which we can check a solution in polynomial time, polytime. Okay, so this is actually, I mean, you think NP, it's a big class. It's anything, it's any problem where if somebody gives you the problem and gives you a solution, you can, remember, you can check the solution in time polynomial in the size of the problem, the size of the piece of paper on which you wrote the instance of the problem, okay? So that's, I mean, there are problems where you can't even check a solution in polynomial time, but most of the stuff that you run into in normal everyday life, yes, it might be hard, it seems hard, maybe hard to find a solution in polynomial time, but if somebody gave you a solution, you could at least recognize it. Okay, any questions about that? So if somebody gives you a formula and gives you a satisfying and gives you a truth assignment that says, this is a solution, this makes this formula true, you can check it. Okay, so that means the set is in NP, complete. Why is it so dark? Complete means if we can solve SAT, in polytime, then we can solve any problem in NP in polytime. Okay, so that means if somebody comes up with an algorithm such that given, if somebody gives you a Boolean formula, if there's a polytime algorithm to tell whether or not it can be satisfied, then for any problem for which we can check a solution in polynomial time, we can also find a solution in polynomial time. What does NP stand for? It does not stand for not polynomial. Okay, not stands for that. It stands for non-deterministic polynomial. So you should have seen non-deterministic finite state machines in second year. Sometimes they're finite state machines, sometimes they're called finite state automata. Okay, so you remember that if they were deterministic, from each vertex, from each node, from each state, you had one, at most one outgoing arrow edge labeled with each character. If it was non-deterministic, you could have more than one outgoing edge labeled with the same character. So in that case, the automaton would accept a string if there were some path from the initial state to a final state labeled with that string. Didn't have to be all paths labeled with that string. So you would get to a state and you'd be, oh, the next character is an A. There are 3 outgoing edges with A. but you would just somehow magically pick the right one and go down it. And so if there were a way on that string to get to an accepting state, a final one of those double circles, you would find it. Magically, you would just somehow do it. So this is the same kind of thing, where you have a computer where non-deterministically, it will just make the right choices, right? It will be like, ooh, here is a problem. Well, I'm going to guess a solution. And just because of the magic of non-determinism, if there is a solution, I'm going to guess the solution. And then what it's going to do is it just has to check that solution, just has to verify. And that it does deterministically. So you can imagine that a non-deterministic machine, what's going to happen is that magically at the beginning, it's given a solution. And if there is, the solution drops from the sky. And if the problem actually does have a solution, this is going to be a valid solution. So it says, oh, here's a problem. I just open my mind to the universe and an idea pops in and I'm like, yeah, okay, now I just have to check that that's true. And I'm so lucky that if the problem has a solution, then it's going to be what I just thought of. Okay, so non-deterministic polynomial. So it's the class of problems that can be done in polynomial time on a non-deterministic Turing machine. We'll see Turing machines next week. Right. So lots of stuff to get through. So you can see that this is a big deal. Cook's theorem says that that is in NP. That's not so hard to believe. Actually, we're not even going to do that because it's kind of obvious. And this says it's complete for NP. If you can solve SAT in polynomial time, if you can recognize Boolean formulas that have solutions, then you can solve any problem that for which you can recognize a solution. Now, technically, we're going to talk about decision problems. So decision problems are things where it's a yes or no. Right? Somebody gives you a Boolean formula and either it's satisfiable or it's not. It's not, so for example, somebody gives you a graph, G, and a number K, and asks you, is there a clique of size at least K? And you say yes or no. That's a decision problem. If they give you a graph and say, what's the biggest clique? That's called an optimization problem. So this is all talking about classes of languages and things like that. So this is decision problems, yes or no problems. Now, it's not actually as restricted as that because you have this thing called self-reducibility, which means that if you can solve the decision version of a problem, usually you can solve the optimization version. For example, suppose somebody gives us a graph and asks us for a small vertex cover. Well, gives us the ability to solve a decision version of vertex cover. So suppose we can solve decision version of vertex cover, VC. So that means they give us a graph and they give us a K, and we can tell, we have this algorithm that tells whether or not the graph. Yes, yeah, well, that's what we think. We think that solving is harder than checking, right? We think that P is not equal to NP. So P is the, so NP is the class of problems for which we can check a solution in polytime. P is the class of decision problems we can solve in polytime. Okay, so the question is P equal to NP? So does that mean that if it's possible to check a solution, if P is equal to NP, then if you can check a solution in polytime, you can find a solution in polytime? People generally do not believe this, right? But Cook's theorem says if you can find an algorithm for SAT, then P is equal to NP. Which means if you can solve SAT in polytime, you can solve any problem for which you can check a solution in polytime. Okay, that will be surprising. And we're going to see in this class, we're going to see why that's true in the next class. We're going to get a hint of that in this class if we keep going at high speed. And then we're also going to see why some other problems are equivalent to SAT. That is, if you can solve, for example, clique, then you can solve SAT, and therefore P is equal to NP. If you can solve three-colorability, then you can solve SAT, and therefore P equals NP. Right. But first, we're going to see why this self-reproducibility stuff. Suppose that we can solve the decision version. So the decision version of vertex cover. So if somebody gives us a graph and a K, we can say whether or not, in polytime, we can say whether or not the graph has a vertex cover of size K. Now, so how do we solve the optimization? Well, okay, let's make it short. Search. Search version of vertex cover. Okay, so the search version, somebody gives us a graph and says, okay, give me and a K, and says, give me a vertex cover of size K. Okay, so what you can do is you have this graph. Okay, so the first thing is if somebody says, gives you the graph in K, the first thing you do is check to see, is there a vertex cover of size K? Because if there isn't a vertex cover of size K, then you can come back and say, look, you're asking me for something that's impossible. If there is a vertex cover of size K, then what you're going to do is pick some vertex. Well, actually, the vertex is in G. So the vertex is in G. You pick some vertex. It's connected to a bunch of other vertices. Okay. Now you say, okay, suppose that vertex, suppose there's a vertex cover of size K, and it includes this vertex B. Then what you can do, if it includes V, then you can say, okay, I'm going to add this vertex to my vertex cover, and I'm going to delete all of the edges incident to V. This is going to leave me with a graph G prime. And now I ask, does G prime have a vertex cover of size K minus 1? If it does, then I can say, great, I just keep going with G prime. If it does not, so if G prime has a vertex cover of size K minus 1, I say, great, V is in my vertex cover. Actually, I can delete V, forget about it. Or I can leave it there because it's isolated, it doesn't matter anymore. If I come back and say, okay, G prime does not have a vertex cover of size K minus 1, then it means V is not in my vertex cover. So what I can do is I can decide, okay, V is not going to be in the vertex cover. I can still delete, so V is now not in the vertex cover. I still delete all of the edges, but now I know that all of the other endpoints are in the vertex cover. So now I can take those, delete all of the edges incident to them. I can add them to my vertex cover and say, okay, so now I'm going to, in this case, I'm going to say, okay, k-3, I'm going to have this g double prime. Okay, so that was a little vague, but we don't have a lot of time in this class. But okay, I think I did a lecture on this last year. So self-reducibility, similarly, you can do SAT. If you can say, does this formula have a satisfying truth assignment? You can then you can use that to like query and say, okay, well, what if I set this variable to true? And you go through and you do all of the adjustments and you say, okay, does this new formula have a satisfying truth assignment? If it does, then you just keep going and you say, okay, that variable was true. If it does not, then you're thinking, oh, the variable was false. Okay, so you can use decision problems to answer certain problems. So this is called self-reducibility. Okay. Now, I think so. Cook's theorem. The idea, the main, I mean, you can sort of get a feel for it. The key thing in this section of the course is reductions, which means you show that if you could do some problem, then if you could do some problem, then you could use it to solve some other problem, right? So you say A reduces to B if we have an algorithm for B implies we have an algorithm for A. So usually what you do is you say, I'm going to take my instance A and I'm going to turn it into an instance of B. Now, this is really easy to get this stuff mixed up. I will do it. You will do it. Everybody does it. Professors who specialize in this stuff do it. But it means that if you could, so if you say, well, we're just about to see that SAT, well, okay, we'll see three easy reductions first, and then we'll see that SAT reduces to clique. Okay, so that means if you could solve clique in polynomial time, you could solve SAT in polynomial time. Okay, and that will show that clique is also NP complete by Cook's theorem, which we haven't seen the proof of yet. And this should just be 2 minutes remaining on timer. Okay, so this should be okay. So I think at the beginning of the course, I said we noted, I'm not sure if we said this, but it's pretty easy to see that. Remember, clique was the problem. Given a graph, is there a subset of, given a graph and an integer k, is there a subset of k vertices such that each of those vertices, every pair of those vertices, there's an edge between, right? So, and I think we said that for any fixed k, you could do this in n to the k time, so it's polynomial. But if k is not fixed, if k is not constant, then we don't have a polynomial time algorithm for it. Okay? We solved this stuff, right? Is anybody there? So I think we saw, and then we saw independent set, right? Which independent set was given a graph and an integer k, is there a subset of k vertices such that for any pair of those k vertices, there is no edge between. And it's easy to see. So clique reduces to independent set, and independent set reduces to clique. Okay, because all you do to reduce clique to independent set, if somebody gives you a graph G and an integer K, then, so this is an instance of clique. Then what we're going to do is turn it into G prime K. This is an instance of independent set. And we say, so does G prime have an independent set of size K? So originally somebody asked us, does G have an independent set of size K? And we say, well, we don't know how to find, sorry, does G have a clique of size K? And we say, oh, well, we don't know how to solve, if we don't have an algorithm for clique, but we do have an algorithm for independent set. So what are we going to do? We just take the graph and complement, which means every edge that is there, we take out, and every edge that isn't there, we put in. So then a clique becomes an independent set, and an independent set becomes a clique. Okay, so we can do this either way. So this is just, we complement the graph. So just every edge that's there is taken out, every edge that's absent is put in. Okay, so you should sort of see that if you have an algorithm for independent set, it gives you this means you also have an algorithm for clique. If you have an algorithm for clique, you also have an algorithm for independent set. Any questions? Reset, start. No questions? People are still here? Okay. Now, it's not quite as obvious to see that independent set reduces to vertex cover and vertex cover reduces to independent set. Okay, so we believe this, right? So you just complement the graph and instances of clique become instances of independent set. So now we say independent set reduces to vertex cover reduces to independence. So this is also pretty easy, not quite as easy, but the key is the complement of an independent set is a vertex cover. So this is actually shouldn't be capitalized because it's not a complement. An independent set is a vertex cover. Right? Why is this true? Because if you take an independent set, well, there are no edges between those vertices, right? So if you take all the other vertices in the graph, all of the other edges are between those vertices. Or, well, okay, not between those vertices, but between, they have at least one endpoint in those vertices. They could have one endpoint in the independent set. Okay, so if you, in the independent, no edge goes between two vertices in the independent set. So every edge either goes between two vertices not in the independent set, or between a vertex in the independent set and a vertex that's not in the independent set. So if you take the complement of the independent set, it has to include at least one endpoint of every edge. Okay. Similarly, if you take a vertex cover and you say, okay, look at all of the things which are not in the vertex cover, they cannot have, if you take the complement of the vertex cover, there cannot be an edge between two vertices that are in the complement of the vertex cover, because otherwise that edge is not covered. Okay? So before we complemented the graph, and now what we're going to do is say, okay, GK, you say, is there an independent set of size K? Well, if this is the instance of independent set, you say, okay, is there a vertex cover of size Gn minus K, where n is the number of vertices? Okay, because there's a vertex cover of size K, sorry, there's an independent set of size K, if and only if there's a vertex cover of size n minus K. I think I'm getting this right. Okay, questions? So you can see, like, and therefore, since clique reduces to independent set reduces to clique, independent set reduces to vertex cover, clique also reduces to vertex cover. Why? Because if we had an algorithm for vertex cover, then, and somebody gave us an instance of clique, we would turn it into an instance of independent set, and then we would turn that instance of independent set into an instance of vertex cover, and we would solve that, so we would get a yes or no, and that yes or no would also be the answer for our instance of clique that we were given. Okay, so if you could solve vertex cover, you can solve clique, you can solve independent set. So all of these three problems are sort of equivalent. That is not terribly complicated, right? So now let's see something that is a little bit trickier. We don't need this, do we? So we're going to see that a problem called free set. So for three set, for three set, we are given a Boolean formula in a Boolean 3CNF formula. So 3CNF, CNF is conjunctive normal form. A conjunction means an and. Okay, so this means is ands of ors. 3CNF means each clause has three variables. So it's something like x1 or not x2 or x3 and x2 or not x3 or x4 and x1 or not x3 or not x4. So this is every clause, these are called clauses, is has three literals, three variables, positive or negative. So this is a not, this is an or, this is an and. And so every clause has three literals, and it's the and of clauses. The literals are ored together, and it's the and of the ors. Okay, so this is called 3CNF. So if we have time, we're going to see that not only is SAT NP complete, this is NP complete, and this requires something called the Satan transform. and maybe we're going to have time for that. So if you believe me that this, you can reduce SAT to this problem, now let's see that you can reduce this problem to clique. Now, clique, independent set, vertex cover, those are all sort of graph problems. They all sort of sound the same. This is a logic problem. So it seems a bit weird that you can take this, you can solve this, if you can solve clique. So this reduces to clique. If we have an algorithm for clique, then we have an algorithm for 3-7. Okay. Now, I'm just going to show you by an example, say that we have these. So what we do is we draw a graph. How do we draw the graph? For each clause, we draw a set of vertices. So this is going to be x1, not x2, or x3. This is going to be x2, not x3, x4. This is going to be x1, not x3, not x4. Okay, so this is actually is going to be what's called a, if you have k clauses, this is going to be a k-partite graph. We're not going to draw any, for each of these clusters, we're not going to draw any edges within the cluster. Okay, what we are going to do is draw edges between the clusters. So in particular, we're going to draw an edge between each vertex and all of the vertices in the other clusters that are compatible with it. Okay, so x1 is compatible with x1. If x1 is true, then x1 is true. If x1 is true, then not x3 could still be true. Those are compatible. If x1 is true, then not x4 could still be true. X4 is not compatible, not x4 is not compatible with x4. So we don't draw this edge. We do draw this edge. We do draw this edge. Okay. So what I'm going to do, because this is going to get very, I'm going to draw the edges. I'm going to draw in red the edges which are not there. Okay. This edge is not there. So actually, I'm going to take these out. Take these edges out. Now remember, the red edges are the edges we do not want. So actually, I guess what I'm doing is I'm doing a reduction from 3-sat to independent sat. So we draw x2, not x2 to x2, not x4 and x4. X3 and not x3. So x1, these are fine. X1 never appears anywhere else. X2 doesn't appear there. X3 like this. X4 and not x4. Okay. So actually, you can see why it was going to get very messy. These are the edges that are missing. We two not x. We have two not x3s. Yes, because we have two not x3s in this formula, and one x3. Okay, so this is actually the complement of my graph. All of the edges which are here in red, the red edges disappear, the other edges appear. Okay, it's actually, I think, easier to draw this. So maybe I'm doing a reduction to independence. Now, what I'm going to argue is if there is, let's do independence set, changing it on the fly. If there is an independence set in this graph with the red edges of size k, oh no. Because then what I would also have to do is to make this the independence set, I would have to draw each of these, which is actually not so bad. I have to draw each of these. When I take the complements of the graph, these are. Okay, so now I'm going to argue if there is an independent set of size k, where k is the number of clauses, then there is a satisfying truth assignment. Okay, so that's what we want to argue. Why is this true? Well, we can't, an independent set can't include any two vertices from the same cluster, right? Because we put all the edges in between the clusters. This is actually easier to draw than the clique thing because, okay, so we're reducing three SAT to independent set. So we can't include anything in the same clusters. Now, if we include this vertex and this vertex, there's no edge between them. So that means they are compatible. One could be true and the other could be true at the same time. Like x1 could be true and not x3 could be true at the same time. Not x3 being true means that x3 is false, which x3 being false, for example, makes this clause true. So if there is an independent set of size k, it means that I have to be choosing one vertex from each of these clusters, which is choosing one literal from each clause, and they all have to be compatible. So I'm going to do this in blue. For example, if I choose this x3, then I can't choose, I can't actually choose this x3. I couldn't choose this one and this one because there's a red edge. But I couldn't choose this one and x4 and not x4. But I can choose x1 and x3 and not x3 and not x3 and x1. These are all simultaneously compatible. So I'm going to claim that if I have x1 is true, not x3 is true, and not x3 is true, x1 being true makes this whole clause true. Not x3 being true makes this whole clause true, and not x3 being true makes this whole clause true. If I can't find an independent set of size k, then it means there's no way to choose a literal from each clause all such that they're all true and they're all compatible. They can all be true at the same time, which means that my Boolean formula is not satisfiable. So the graph without these three thingies, without these blue edges, this graph has an independent set of size 3, if and only 3 being the number of clauses, if and only if this formula has a satisfying truth assignment. And this works for any 3-SAT formula. Okay? So that means if we have an algorithm for independent set, then we have an algorithm for, so if we have an algorithm for independent set, then we get an algorithm for 3-SAT. And therefore, since if we have an algorithm for clique, we have an algorithm for independent set. If we have an algorithm for clique, then we also have an algorithm for 3-SAT. So you can see I need more board space. We had clique. This is, remember the map I drew at the beginning of the class, at the beginning of the course. So you have clique, you have independent set, you have vertex cover, then you have 3 sat, and we saw that clique goes to independent set, and independent set it goes to clique, and independent set turns into vertex cover, and vertex cover turns into clique, turns into independent set, and now we've just seen that 3 sat, we can reduce 3 sat to clique. Okay, could you say that again? G has an independent set of size 3. If that particular graph had an independent set of size 3, if and only if this particular formula, 3-sat formula, has a satisfying truth assignment. Okay. So now we want to see, I'm going to show you that clique, if you can solve sat, not 3-sat, it's true of 3-sat, we're going to get there. I'm going to introduce this other problem, which seems more powerful, which is sat, which is just Boolean formulas. Given a Boolean formula, does it have a satisfying truth assignment? And now we want to see this edge, which I'll draw in red. I'm going to sketch that clique reduces to sat. And this is going to give you an idea of why Cook's theorem is true. Because sat is really powerful. You're going to see that sat is like a programming language. In fact, if you've seen Prolog, then you can believe that it really is a programming language. You have some idea of how to use logic as a programming language already. Has anybody seen Prolog? Do they teach Prolog anymore? Yes. Wow. It's still around. Okay. So if somebody gives me a graph, and so actually, sorry, we saw 3-sat to independent set. It's usually presented as 3-sat to clique. We did it as 3-sat to independent set so that I didn't have to draw all those lines and it wouldn't be so confusing. Okay. Let's see clique to sat. So somebody gives you a graph G and an integer K. So we're given GK, and we're asked does G have a clique of size K? Okay, and what we want to do now, before we took a formula and we turned it into a graph, now we're going to take a graph and turn it into a graph and an integer and turn it into a formula. Now, it's not going to be a 3-sat formula because we may or may not get to Satan transform today. Okay, so how are we going to do this? Well, suppose that the vertices V equals V1 up to Vn. Okay, so now we're going to establish literals. So x1, well, xi is an indicator variable. And it's true. This is how to think about it, but we actually, like, you can't insist on this. You have to write the formula in such a way that it's satisfiable if and only if the graph has a clique of something. But think of it as xi is true if vi is in the clique. False otherwise. Okay. So for each variable, for each vertex vi, you have this xi. Okay. So now, suppose you have suppose vi vj, this edge, is not in the graph. So suppose edge vi vj is not in the graph. Then you can't have xi, you can't have vi and vj both in the clique, because then it's not a clique, because they're between two of the nodes in the clique, there's a missing edge, right? So what you're going to say is not xi and xj. So you're going to have in your formula, you're going to have something that says, if this edge isn't there, then you can't have both of these. Right? So you just go through, and oh, and the other thing, this is going to have to remember all this stuff. So you just have to go through, and yeah, I think that's enough. And then it's XOR. It's not the case that they're both true. Yes. So they can both be false. One of them can be true. One of them can be false. It's not going to work if you say, okay, if there is an edge, then they both have to be true. That's not true, because you can have an edge and one of them is in the clique, but the other one isn't. Right? The only thing you can't have is if you don't have the edge, you can't have them both in the clique. And then you have to write a formula that says you need a clique of at least size k. So you want to somehow say that if you sum up all of these xi's, that I could have just paid attention to the fire hydrants like that, or whatever this is. Okay, so what we're going to do, we want to write a formula that says, need a formula that says at least k xi's are true. Okay, so what you do is, now this is actually going to use quite a lot of extra variables, but you're going to say y ij is true if true. You want to come up with these extra variables if at least k of x1 xi are true. Actually, I have to say, people usually don't go through this, because usually you get Cook's theorem and then people say, well, you don't have to do this. Clique reduces to sat because of Cook's theorem. But I think it's easier for you to understand Cook's theorem, why Cook's theorem is true, if you see that we can take clique and we can write the formula. Because after you've done this a couple of times, you get the feeling you're like, yeah, Boolean formulas are pretty powerful. If I'm given a problem, then if I'm given a problem where I can recognize the solution in polynomial time, then I can probably write a formula that sort of says this has a solution. It's going to be polynomial size, and then it's an instance of SAT. So, and that's sort of how Cook's theorem works. It says, okay, given any, you actually prove that given any problem where you can recognize, then you sort of take it and you turn it into machine language, and then you turn that into a SAT formula. So I think it's easier if you go this way. How are you going to get this yi is true if at least j of x1 to xi are true? Well, that's going to be the case. You're going to say y11 if x1, actually in general, yi1, well, okay, y11 if x1, yi1 if either xi or yi minus 1, 1. So this is for I greater than 1. Right. So this feels a bit like dynamic programming, doesn't it? Right. So so this, if you can write if using a Boolean formula, right? It's just a double implication which says, like, if this, actually technically this is an if, so it's a bidirectional implication, and you're just saying, okay, it's not the case that one of these things is true and one of these things is false. Either they're both false or they're both true. And you can write that easily. You did learn that in second year. I assert that as true. I have to reset this. And I am not going to get through all of this stuff I wanted to get through today. Yeah. Okay. So you say, okay, y11 is true if x1 is true. y1 I1 if xi, or so if this is true, then I can get at least one thing true. Or if I can get at least one thing true, and you say, okay, y ij if either y I minus 1, so j minus 1 and xi, or y or y I minus 1j. Feels a lot like dynamic programming. Huh? Right. So you can write this and you say, okay, how many variables is it going to use? It's going to use like a quadratic number of variables, right? Because now I need one of these variables for sort of each cell in my matrix. And then eventually I'm going to say, okay, so I write this, and then in my clause, I'm going to say all of these things are true. And then I'm also going to have ... and y y n k. So I can get, I'm appending this to my formula, and I'm saying that at least k of my n indicator variables are true. So this is not too hard. I mean, if you think about it, like, how would you write it? You could write a formula that's saying, yeah, okay, this is so xi is true if you can put this thing in the clique, and then you just need to write this formula that says this. I wrote this up, I'm sure, last year, so it should be in the scribe notes. Okay, so that's this arrow. We can reduce clique to SAT. So if somebody gives us a graph G and an integer K and asks us, is there a clique font size K? We don't know how to solve that in polynomial time, but we can turn it into a formula, a Boolean formula. In polynomial time, we can turn it into a formula such that the formula is satisfiable if and only if the graph has a clique of size K. So that means if somebody gave us a magic box of like this Oracle thingy, and it would answer instances of SAT and say yes or no correctly, then, and somebody wants to solve an instance of clique, then we can turn it into an instance of SAT, and then we can use the magic box. So clique reduces to SAT. And we saw that SAT reduces to clique. So now, this is no longer in doubt. Clique reduces to SAT. I don't think we are going to get time to fill in this arrow today, but it will go into the lecture notes. Okay, so let's see. We're not going to see. So basically, I'm going to draw in some of the other stuff. I hope you remember what it means for something else. So you also have, remember from when we drew this cool diagram at the beginning of the course, just checking that this is recording again, because I'm so apparently. We also had hand-pad. We had three-color ability. We had planar three-color ability. We had four-color ability. Now remember, planar four-color ability, planar five-color ability, planar six-color ability, they are not hard because planar four-color ability is always just yes. If it's a planar graph, it's always four-colorable and or five-colorable or six-colorable, whatever color. Except it's hard for three. So remember, two-color ability is easy for planar and non-planar. Three-color ability is hard for planar and non-planar. Four-color ability is hard for general graphs, but easy for planar graphs. So obviously, if we can solve three-color ability, we can solve planar three-color ability because you just ignore the fact the graph is planar. So if you have a magic box that tells you whether or not a graph can be three-colored, you just don't tell the magic box that it's a planar graph. So clearly, this is true. And we saw in class, actually, let's move three-color ability over here. We saw at the beginning of the lecture, right? So if you wanted to reduce three-color ability to four-color ability, you just added another vertex and made it and attached it to everything. So now if the original graph could be three-colored, then you can four-color this new graph. And if this new graph can be four-colored, then this new vertex has to be a different color than everything else. So you just take it off and the remainder is three-color. So three-color ability reduces to four-color ability. Planar three-color ability reduces to three-color ability. What I'm probably, how much time do we have? Not a lot. So then actually all of this stuff, they turn into big cycles. You can reduce hand path to three sat. You can reduce you can reduce hand path to sat, you can reduce sat to three sat, you can reduce three sat to hand path. Actually, you reduce three sat to directed hand path and you reduce directed hand path to hand path. You can reduce four-color ability to sat. Now, what we're going to see next, I want to show you this one because this is cute and easy. But the one we're going to do now is that three sat reduces to three-color ability. Okay, so if somebody gives you an instance of three sat, then you can turn it into a graph G such that G is, so somebody gives you a formula. Someone gives us a 3CNF formula, Boolean formula, F, we can build a graph G such that G is three-colorable if and only if F is satisfiable. And I hope that doesn't take us 15 minutes. Okay, so does anybody remember what this cute little formula was that I used for cleat? If somebody could write that in the chat, that would be great. So running out of board space. But the idea is, what we're going to do is we start with a triangle. And we're going to call whatever color this vertex gets, we're going to call that color true. And we're going to call this one false. And we're going to call this one base. Okay. And then for each literal in the formula F, so we're going to have x1 and not x1, and x2 and not x2. And there was, I'm going to write base over here so that I can have base. And I can have x3, not x3. x4, not x4. Okay, so does everybody see that if you want to three-color this, true has to get a color, false has to get a different color, base has to be a different color than all of those, than both of these. And that means one of these have to both be different colors than each other and different colors than base. So one of them has to be the same color as true, and one of them has to be the same color as false. So that's sort of forcing us to color our literals. The literal is the positive. Literals are positives and negatives of the variables. That's going to make us color these things correctly. Now, what we're going to have is for each clause, nobody wrote the formula in the chat. Does anybody remember what it was? Okay, I'm going to do it again. Well, so let's say that we had x1 or what was it, not x2 or x3. So what we're going to do is write a little. Now these are connected. This, when I write x1, it's actually this x1. Okay, this vertex, I'm just writing it twice, but it's actually all connected. Okay, it just makes it hard to draw the stuff. But actually imagine that these two circles are this. And not x2 and x3. I really miss having physical classes. Like I don't know. I look and it's like I see nobody's writing. Or people. Okay, so what you do is you sort of make a graph that I'm trying to remember. Best to say. I think I have this written down. Oh, right. X1 or not X2 or X3. Okay, so I did remember it correctly. Just let me see what you do. Yes, okay. And then you do this. And this. Yeah. So, if this is you're just gonna have to trust me that if this, one of these, if all of these are false, remember, all of the literals have to be true or false. So if all of these are false, so let's say false is red, right? So if x1 is red, so if base is blue, 10 minutes. Then, so let's say true is green, false is red, base is blue. So now we're going to say x2 is also, not x2 is false. So if all of these are false, x3 is false. So if all of these are false, then one of these has to be true and one of these has to be base. Okay? It doesn't really matter which one is true and which one is base. Where is blue? Because it means this one has to be false. So if this is false and this is false, just a sec. Yes, oops, sorry. Too many pens. This has to have another of these. Okay, so if this is false and this is false, one of these has to be true and one of these has to be base. Let's just reverse the order for fun. And that means this has to be false. Right? So if these are all false, this has to be false. I hope I copied it. It'll be in the yeah, but I just needed the first one. And I'll check the formulas before I type up the course notes. Don't worry about it. As long as people sort of believe that if these three things are false, then the output has to be false. Now, let's suppose that one of these is true, right? So, so I'm going to switch this, and I'm going to say x3 is true, not x3 is false. So that means x3 is true. Now green, don't know if you can see that this is green, but it is green. So now this still has to be red. But now we have a red, we have a green. So we can put a red here. And we can put a blue here. So we can put a true here. So you can go through and check that if all of these are false, this is false. If 1, 2, or all 3 of these is true, then this can be true. Okay, so then I just have to look again because I didn't actually remember. Yeah, okay, so this is. So then what we do is we take this and we connect it to the base, to this vertex. And we also connect it to false. So that's saying this has to be, for this graph to be three colorable, this has to be the same color as true. So therefore, it's saying this graph is three colorable if and only, and you do this for every clause. So remember, these three things, this x1 is this. So it's not like hanging off, it's not a separate graph. And this base is this. So now you get this graph that's three colorable if and only if your formula is satisfiable. So we have that 3-sat reduces to three colorability. If there exists a polynomial time algorithm for three colorability, then there exists a polynomial time for 3-sat. And so I'm going to put in dashed lines of all of the other things that I would like to show you today that we're not going to have time, but you can read about them on the internet. So I'm not going to, so three colorability, I'm not going to show that. What I am going to, Satan transform will be in the lecture notes. You can do this reduction. Like obviously, if you can solve SAT, you can solve 3-sat. That's trivial, okay? Because 3-sat is a special case of SAT. This is easy. To actually reduce SAT to 3-sat, you need this Satan transform, which I showed, somehow I had time last year and the year before. So now what we're going to see in the remaining 4 minutes, yeah, maybe, is we're going to reduce 4 colorability to, we're going to get this stuff out of the way so I can draw the arrow. We're going to reduce 4 colorability to SAT, which is again one of these things that people don't usually see, because this arrow just follows from Cook's theorem. But since we haven't seen the proof of Cook's theorem, I want you to understand sort of how SAT is powerful enough that SAT can be NP complete. If you can do SAT, you can do any of these problems. So the answer is, so now somebody gives us a graph G. G, we can build a formula, a SAT formula, a Boolean formula F, such that G is, actually, I don't have to reverse this order because it's an if, so the implication goes both ways. So F is satisfiable if and only if, but now I want G is 4 colorable, okay? In fact, this would also work if it were 5 colorable, 6 colorable, whatever, okay? So what do you do? Again, for each vertex, you have it, well, now for each vertex, you have 4 indicator variables, okay? So you have, for each vertex BI, we have, let's say, RI, BI, and GI, okay? So RI says that RI is true if and only if VI is red. BI is true if and only if VI is blue. GI is true if and only if VI is green. Okay, so what we are going to have is RI implies not BI. I hope you know how to write implications as logical formulas. RI also implies not GI, BI. So BI implies not RI, just in case. BI implies not GI, GI implies not RI, GI implies not BI. So it can't be 2 colors at once. I'm out of time. I can put this on the next assignment or something. Okay, just finishing. So what you're going to do is for each vertex, you write these formulas that say, okay, it's a color, it's not 2 colors, it's not 3 colors. Oh, perhaps this would be 3 colorability. And you also need some, for 4 colorability, you have yellow. Okay, and you also have yellow in here. And so you say, okay, it's one of the 4 color, each vertex is one of the 4 colors and only one of the 4 colors. And then for each edge, Vi, Vj, you write Ri implies mod Rj, Rj implies mod Ri. Okay, so you just write out the little formulas that say, if you have an edge, it's not true that these 2 vertices are the same color. So now you get a big formula, but it's not too big. It's still only polynomial size. And it says this graph is 3 colorable. Okay, the formula is satisfiable if and only if the graph, 4 colorable. Graph is satisfiable. And you could do this for 5 colorable, 6 colorable, whatever, right? So 4 colorability reduces to 7. Okay, so that sort of gives you an idea of why SAT is so powerful. So questions? That was all totally clear. Woo. I thought it was a bit fast, but if people thought that was the right speed, that's great. Is anybody still here? I'm down to 12 people. Yes, it was totally clear. Okay. Or yes, you have questions. Well, yes, I am here. Oh, okay. So I hope the lecture notes will be clearer. You can see why this stuff is kind of cool, right? I mean, you're getting to see like all of these things, all of these paths, they all lead back to here. All roads lead to 3SAT. So you can see I managed to get to, I didn't get 3 colorability to planar 3 colorability. I got 3SAT, I didn't get 3SAT to 3, I did get 3SAT to 3 colorability. I didn't get SAT to CNF SAT, I didn't get CNF SAT to 3SAT. I did get K colorability. So I got maybe 2/3, 3/4 of what I wanted. It was fast, but I got most of it. There are whole books about this. Oh, I wanted to show you. So this is this is a famous book by everyone just calls it Gary and Johnson. But this was published a couple of years after Cook's paper. So a guide to theory of NP completeness. Actually, I crossed his name out. But I got this book from one of my professors at University of Toronto because I helped him clear out his office because he was retired and they were moving into a smaller office. So he let me pick some books and I picked this one. So I don't know if anybody, JNP Hume. So Hume he used to be for a long time the host of The Nature of Things. So he was David Suzuki before David Suzuki was. Does David Suzuki still host The Nature of Things? But this guy was like David Suzuki a long time ago. And I got his copy of this book. So I think he actually got one of the original ones. I don't know when this was published. So yeah, this lists thousands. Okay, maybe not thousands. There are thousands of problems which are all like this. It's like if you could solve one of them, they all fall. They're like dominoes. But if one stands, they all do. Yeah, it's a good book. So it has, it's got some neat stuff. Well, for example, it goes into much more detail. There are also, there's NP completeness stuff in Introduction to Algorithms, but if you want to get into this complexity theory stuff, I would recommend The two I learned from were, this one's by Sipser, and this one's by Lewis and Papadimitriou. So Introduction to the Theory of Computation and Elements of the Theory of Computation. And, but yeah, this is a client, like everyone says, Gary and Johnson, because what happened, Cook wrote the paper, and then like shortly afterwards, Karp, so Cook showed that 3-sat was NP complete, and then Karp, I think it was 12 problems, showed that it showed that clique is NP complete, and a bunch of like 3 partition. So that canoe problem, the canoe problem of like putting people in canoes, if you can put 3 people in the canoe, then it becomes really, really hard. But it's not NP hard, it's NP hard in the strong sense. And we'll get into the strong and weak sense in the next class, maybe the class after. I can't believe I'm trying to get through all of this in just 3 classes. Okay, but everybody can go because I'm way over time. Okay, I'm gonna stop the recording. Cheers. Recording, stop the recording. Yes.